So welcome back. I am more alive today than I have been in a while. Yay. Oh, wow. I think we have everyone. No, we're missing one person. Our class got big. We have lots of people. This is so great. Okay. So to announcements. Today, this is the announcement I just put out. So today we're gonna go back to the slideshow we did in week 1, and we're gonna go over the last few slides there to talk about specifically 2-level models and a little bit of 3-level models, but we're gonna focus mostly on clustered models, not longitudinal models today. We'll hold off on those for a little bit. The math works much the same way, but it gets confusing if you talk about both of them first right off the bat. So we're gonna look at that slideshow, and then the second slideshow we're gonna look at has the equations. A lot of people were saying, reading this wasn't so bad until the equations and all those letters with all the subscripts just went, whew, right? So this is gonna help us break down those equations. And then next class, and Thursday when you come back, we are going to walk through chapter 2 in Hox's book, his examples in R, what the syntax looked like and how you interpret it and what all the numbers mean for those examples, okay? So today is more of a conceptual day. So hopefully you guys have already read chapter 2 in Hox and were able to watch those first 24 minutes of the MLM video. And you can skim the additional material if you would like. It gets kind of bogged down in SAS and SPSS and Stata. But the discussion post is not technically due till Thursday. So I know a few people have started putting on the discussion post, so go ahead and remember you have to do your original post and comment on at least somebody else's. And then next Tuesday, a week from today, homework 2 will be due, as well as a discussion post that goes along with homework 2. So homework 2, just to go over this so you know what you're doing for homework, this new homework is you're going to search for 2 journal articles in an area that you're interested in. So everybody, different areas, but they should include multi-level analysis. So you need 2 of them. One to use cluster data, the second one to use hierarchical, or one to have the clustered hierarchical data, the other one to have longitudinal or repeated measures data. They have to use multi-level or mixed effects models. Sometimes you have both clusters and longitudinal both going on in the same data set analysis. If you find a paper like that, you can put it for either category you can choose. So if you go to Google Scholar, you can type in the name of a journal you know is high quality in your area, or search terms for the things that you're interested in studying, and then add in multi-level model or HLM or mixed effects or random effects. This is not anything, repeated measures ANOVA does not count. It has to be mixed effects regression somewhere in the analysis portion of the paper. So you're going to have 3 things to upload. You're going to have to get the PDF version of those articles. So if you need an electronic PDF copy of the articles, do not pay for anything. So this can be an article you already read, one that you were hoping to figure out by taking this class, or go searching for a new one. You can ask your mentors, but you need an electronic PDF copy of it. I do not want anyone to have to pay for this. So if you use Google Scholar on campus, or you sign in with your university account, you should be able to get anything that the library has access to. And so you need to upload for your assignment, upload a copy of each of your 2 articles and then a knitted version of the R Markdown. Now, the R Markdown file asks you to answer some questions about each article. Sometimes the questions, like one of the questions is, what software did they use to analyze the data? Articles should include that. But what if your article doesn't? It happens more often than I would like. Then you just write, this article did not tell me what it used to do the analysis software-wise, okay? So if it doesn't give you the information I'm asking about, tell me that it didn't give it to you. Don't just leave it blank. So there are two files for you to download. One is the R Markdown that you type into and knit to upload with your two articles. And then this is one that says directions. Is that same RMD already knitted before you type in it? So it's a little easier to read. So you're going to fill out questions about journal article 1 and 2. 1 is the clustered one. 2 is the longitudinal one. So the questions are mostly the same. What is the article title? What's an online link to get it? What was the sample size? How many groups or clusters are there? What's level 1 units? What's level 2 units? Was there a third level or more? What's the dependent variable? What are the covariates? What software did they use? What method did they use? And what are the results that they reported? Did they use plots? Did they give effect sizes? Those kinds of questions. So that's all the questions for Article 1. Article 2 is mostly the same thing. They're just tailored a little differently for longitudinal. And that's assignment number 2. So this one's very little software usage. You're just going to be typing sentences in, okay? So no code writing for this homework assignment number 2. Is that good news? Assignment number 3, you start doing multi-level models in R, which is what we're going to start learning on Thursday. Okay. So anyone have any last minute questions on homework 1 about the linear regression, multiple linear regression in a single level? Okay, we had great office hours the last 2 days. Those of you that came, I think that was worth our time. So I'll try to set those up. I don't know that we'll need a ton of office hours in the next week because there's no real software usage. But if you want to have a Zoom call with me in the next week, just send me a quick email. We'll find 10 minutes, whatever, when it works for both of our schedules. But I don't anticipate having any office hours for the next weekish, unless it's requested. Okay, so again, that's what's due. That's what's you should be working on. This is what we're going to cover. So let's go into PowerPoint. What did you guys think of the reading? What about the video?
The video was a lot easier to follow.
You like the video? That video series is very well done. It's very professional. It's very succinct, but detailed, I think. If some of it was like flying over your head, don't worry. That's okay. That was our first introduction. Okay, so this is that first PowerPoint that I made for the workshop. I think this is about slide 8 or 9. 9? We left off. So the advantages of multi-level modeling over doing something like single level regression or repeated measures ANOVA, given that you have clustering in your data, whether that's hierarchical clusters or longitudinal repeated measures. Number 1 is if we have dependency and we ignore it, we ignore the fact that the students are clustered in classrooms, we ignore the fact that the patients are clustered at different therapists, we ignore those facts that we have repeated observations and treat them as independent, we might get, at best case scenario, our betas will be accurate, but the standard errors will not, and so our p-values may be dead wrong, and nobody will be able to replicate our work. So a lot of the time we treat the correlation, like students in classroom, we treat it as a nuisance and we just control for the fact that there are clusters or groups. And we don't really want to study the dependence. Like in longitudinal, we know that repeated observations on the same person are correlated, but we want to look at the other variables correctly. And so we have to alter our assumption of independent residuals so that the lack of independence of residuals can be treated as a nuisance, or it can be the phenomenon, or the whole point of the research. And we'll see examples of both of these as we go forward. So let's think about grouped or clustered data. in any of those, and it can be meta-analysis, latent variables, hierarchical data, longitudinal, clustered or complex surveys, and all of those. The key is that you do not have independent observation, that there is some level of correlation in our observations. The ICC, and this is wrong on this slide, it's the not the intra-class correlation measures, and it's right here on this slide down here, the intra, it's just the top of the slide that's wrong. It measures to what degree is our data clustered. So if we think about students in classes, are students different from each other? Yes. Are classes different than each other? Potentially, yes, because of some shared environment, the teacher, the way that the group, I mean, if you've ever taught anything or been in a class, you know, it's just different depending on the whole group dynamics and the time of the day and all these, is it too hot in the room that time of day, etc. So we know the person in the hierarchical design of students in classrooms or patients and therapists or nurses in hospital wards, there is always some degree of clustering. Now, the one extreme is that there is no class-to-class variability, zero. The ICC is zero. And this is the case if there is no role of clustering. So if we have two kids in the same classroom versus two kids in different classrooms, if there's zero shared environment, then the correlation is the same between kids in different classrooms and kids in the same classroom. That would be an ICC of 0. An ICC of 1 is the other extreme, and that's where all members of the cluster are identical. So this is way too extreme. It doesn't really happen in the real world ever. But think of a school where you had, say, 3 classes. And in one class, the teacher wrote the end of level test. So she taught the test. So every kid in her class got 100%. And then another class where the teacher had some medical emergency left and they didn't get any of the information. So everyone in that class got a 0. And then you had a third classroom where the teacher thought she got the test, but it was a fake test and it had half the wrong answers. So she taught it to her class. So everyone in that class got 50%. So in that case, everyone in each of those 3 classes gets exactly the same score. So there's a perfect correlation in this classroom. In classroom A, everyone got 100%. In classroom B, everyone got 50%. In classroom C, everyone got 0. How many data points do we have there? Just 3. It doesn't matter how many kids are in each classroom if there's no variation within class. It's all class-to-class variation. So that's the extreme of an ICC, an intra-class correlation of a perfect 1.0. There's no person-to-person variability. There's only class-to-class variability. And the other extreme of an ICC of 0 would be there's only person-to-person variability and there's no class-to-class variability. It's basically classes don't exist. In the real world, the ICC is somewhere on the spectrum between no correlation and perfect correlation. And there is no right amount of correlation. It is just what it is. It's descriptive in nature. Linear regression is going to treat the ICC as perfectly 0 that we've learned. So now we're going to learn multi-level modeling that allows the correlation to be more than 0, but not necessarily 1. Now, here's a little teaser. When we go to do power analysis, the needed sample size you need depends on what? There's some ingredients that go into every power analysis. To know what your sample size should be, you need to input into the algorithm the type of analysis you're going to do. And Carly, you unmuted. What else?
Effect size.
Effect size.
The estimated power.
Estimated power you want to achieve. And usually a significance level, and that's
right.
equals 0.05. And we usually go for beta of 80% power, 0.80. But you have to put in effect size. ICC is part of the effect size for a multi-level model. And we never know what it is before we gather some data. So if you don't have pilot data, there's no way to guess what the ICC is because it's different in every situation. In a lot of education research, it hovers, kids in classroom hover somewhere between 10 and 20%, 0.10, 0.20, but it can be very different depending on the size of the classes, the role of the teacher, how much the shared environments vary from class to class. Are these all classes in the same district or are they across the nation? So you can have, there's no right ICC to plug in by default. And this is what makes power analysis so difficult. In your reading, okay, let's go to the Hawks book for a second. So on our main Canvas page, you can click on the Hawks book to take you to the library page. And, oh, I've been timed out, so I gotta sign in. Now, Carter, was it you that couldn't read for more than 2 minutes before it logged you out?
Yeah, it was 5 minutes. And I think you can see, so under availability, it has your institution and has access to one copy of this book. So
Okay.
I think that means that only one person can be viewing it at a time. And then anyone else who tries to get on, they put a 5-minute limit, which is kind of funny for a stats book.
That is really unfortunate. When we had this, the 6600 textbook, I don't think we had that limit. I'll see if I can download some chapters, but you might want to think about getting a hold of a copy if that's going to be a big issue. I'm going to go into read online though, and I'm going to go to chapter 1. There are some nice things about the electronic version. So in this chapter, which I love, chapter 1, it talks about, when it's talking about sample size here. So if you have a sample of 10 classes with 20 students each, how many data points will you have? 10 classes of 20. 10 times 20 is 200. So you have 200. But do we really have 200 independent students? No. If the ICC is treated as 0, we have a sample size of 200. But if the ICC is perfectly 1, our sample size is 10 because we'd have 10 distinct classes. Our effective sample size is somewhere between 200 students and 10 classes. And where it falls, is it closer to 200 or closer to 10? Depends on the ICC. And so that's why they give this V effect, the effect size. It depends on this row. See that kind of almost a P Greek letter row? That's the symbol we use for the ICC. So the effective sample size depends on not just how many clusters and how big each cluster is for total number of observations, but to what degree are the clusters similar, units similar within clusters compared to different between clusters. And that's the idea of the interclass correlation row. And it's going to come up over and over and over again. So there's kind of a touch to that. Okay. So if we don't do a multi-level model, what are our options? One of the favorite options is aggregating, averaging, just averaged by clusters. But in that data, if I had 10 classes of 20 students each and I did class averages, what's my sample size if I aggregate? Is it 200 anymore? Instead of having 200 students, if I average, I'll only have sample size 10. And so we've thrown away a lot of information. Now, if everyone in a class or a group is identical, well, you should use only sample size 10. But usually it's throwing away information because, yes, clusters are more similar to each other, members inside of a cluster, but there's still variation between members of the cluster. So the idea of doing the averages can produce something called the ecological fallacy. And this is where the trend you see in the averages is different than the trend you see in the individual data. And we'll see there, I think there's lots of examples in Hawks chapter 1 of the ecological fallacy. The other option is this I see done a lot. People have learned regression in their first year stats series, and they know how to do regression, and they fit a regression model to students and ignore the fact that they're in classes. What if one of my predictors is the number of years the teacher has taught? Everyone in this class has Mrs. Smith as a teacher, and if Mrs. Smith has taught for 40 years, what is my value for teacher's experience for everyone in that class? It's exactly 40. Everyone gets the exact same number 40, even though the number 40 is the years for the class as a whole, not a value for each person in the class. And so to disaggregate means to treat a cluster level variable as if it was a lower level micro unit variable. And the way this screws up your analysis is, one, we have clustering, not independence, and two, that covariate that should be for the macro cluster unit that we're treating as a micro level unit variable. Everyone in the same cluster has the same value. They're exactly homogeneous. There's no spread. And so the standard errors get screwed up because of it. And this is why if you have clustering, you don't want to do regular old regression like we did in homework 1. You need to learn what we're going to learn in this class. I'm so excited for you. It's so great. If you ever run into a problem with a colleague, a mentor, a committee member, a reviewer in an article, this is a really good article to cite and to share and to start with. If you're used to doing ANOVA, especially repeated measures ANOVA, about why multi-level modeling is a better way to go. And here is some of the last few sentences. The simulation suggests that multi-level yields higher power. We all want higher power, right? You only have money and budget and time to get your sample. Might as well squeeze everything out of it you can, particularly under realistic circumstances. Although technically complex, what we're learning is not simple. This is not a 1-hour class, right? This is a whole 3-credit semester class. It's technologically complex, but it is very useful for analyzing repeated measures data, and specifically here is for speech research. And so over here the bullet points are listings of the high points for multi-level. So there's no sphericity assumption. The sphericity assumption assumes that repeated measurements are all equally correlated. So if we go back to our homework, here's the homework. You guys remember this plot? Pop it out. No, it didn't make it any bigger. That's not fun. Okay, so the correlations on the diagonal. The diagonal itself is always correlation 1, so it's not shown. So right off the diagonal, we have on the bottom the numbers for the correlation, and the top they're shown as circles, and the size and the darkness of the blue is how close to 1 they are. So the correlation between observations that are only made 2 months apart. So between pre-score and 2 months, between 2 months and 4 months, between 4 months and 6 months, 6 months and 8 months. Those observations that are really close in time, the correlation is quite high. The correlation is like 0.8-ish range. But what happens is the correlate on that matrix as we move farther from the diagonal. Look all the way out to the outer corners. The correlation is only 0.38. That's the correlation between the very first and the very last observation. When you have repeated measurements in time, repeated measurements that are close in time are usually more highly correlated than observations that are made at the very first and the end. The farther apart in time observations are made, usually the less correlated they are. So this is the pattern of fading off. This is correlation decay. If you were to analyze this data with repeated measures ANOVA, it would treat that matrix as having every number in it identical. That's the sphericity assumption. How likely are you to violate that in real data? Almost always. Now, assumptions, we're never going to meet them perfectly, but the more you violate the assumptions, the more your model is going to give you faulty results. And the only way you know that your results cannot be trusted is if you check the assumptions. So with multi-level models, there is no sphericity assumption. We don't have to assume they're all equally correlated, all the different time points. It allows for more complex sampling designs. We can choose classes and randomize at the class level and then choose all the students in the classes. Or we can randomly select hospitals, and then within each hospital, we'll randomly select wards, and within the wards, we'll randomly select nurses, or treat it as such. We can include unequally spaced time points. In repeated measures ANOVA, it always treats the time points as being equally spaced. That's not real life. A lot of times we have a baseline, a mid, and an end, and then we'll have a delay, and then a longer follow-up. That's a really common design. Another thing is repeated measures ANOVA treats or assumes that you have complete balance, that your groups are equal sizes. With attrition with human subjects, that's rarely the case. Even if we try, they end up being not equal sizes. And this last bullet point is big and often overlooked. We can have covariates that apply to the individual or to the group or both, and they can interact with each other, called a cross-level interaction, which is not something you can do in repeated measures ANOVA. You can only do individual level covariates with ANCOVA. So there's all the beauty of multi-level models. Why do we not use them more than we do? Number one reason is lack of training. Oh, you guys are gonna check that off your list, right? You're gonna be trained. And the reason lack of training, yeah? Oh, it's just feedback. The lack of training is because this class comes after the standard series, and a lot of people don't have room in their program of study. You guys got it in, yay. It can, the second bullet point, it can be difficult to learn. This can be technical. There are a lot of moving parts. You're gonna feel like you're drowning the first week, more than likely. That's okay, because we're fighters, right? We're gonna fight through it, and we're gonna get it all broken down, and we're gonna do lots of examples so that you can learn this, because you guys can. You can totally master this. In the past, there's been lack of software. R makes this easy. I've tried to do multi-level models in lots of software. SAS, it can be a bear. SPSS, it is nearly impossible. I tried for 8 years when I was doing the memory study because my bosses loved SPSS. And I tried, and it's not worth the hassle. Because you can, has point and click, but there's so many options, the menu you get lost in, and then you end up getting it wrong. I published multi-level modeling in my first paper. I'm not ever gonna tell you the citation because I don't want you to look at it because it was done so poorly. And this last bullet point is always gonna be a struggle. For multi-level modeling, having one of the things that is offsetting from it, you know, I've told you it's all almost magical. The downside is you need a good sample size. So it's not good enough to have 200 students if they're only coming from 2 classes. You need a good number of each level. So you need a good number of students in each class, but you also need a good number of classes. If I want to study students in classes in schools, I need to start out with a good number of schools, say 10 or 15. And within each of those, I've got to have a good number of classes. And within each class, I need a good number of students. You need a good number. And that depends, what's good enough depends on the ICC and the effect size, which you only know from pilot data, really. Okay. Comments, concerns? So quiet in here. Examples. Okay, so here is one scenario. It's called a 2-level model. This is 2-level structure, where we have level 1 is always the micro, lowest, smallest units. And this is where your outcome must be measured. That's not a should, but it's a must. Your outcome has to be measured on the smallest micro level 1 units. So if we have individuals, and then the individuals, if they are nested or can be grouped into other macro or larger units or clusters, that would be a level 2. So we might have people, but they belong to certain neighborhoods. So the people would be the level 1 units, and the neighborhoods would be the larger level 2 units, and which the level 1s belong to. So sometimes this is hard when you have to brainstorm for new situations. How many levels do you have and what are the units of each level? And it can be complex and it's good to brainstorm it. Your predictor variable, so your outcome has to be measured at the lowest level. Your predictors can come from any level, one, the other, both, and interactions between level 1 variables, level 2 variables, and cross-level between level 1 and level 2. So an individual variable might be the individual's socioeconomic status as measured by their income. But then the neighborhood as a whole might have the socioeconomic status of the whole neighborhood. So we can have the frog in pond scenario, where you might have in one neighborhood, someone who makes 60 grand is the richest person, but in another neighborhood, they're making 60 grand, they're the poorest person. So you have straight up how much each person makes, but you might also have the general status of the whole neighborhood, because that might also play a role. Or you could have something different, like, is there a neighborhood watch? That would be a neighborhood level variable. Like if we were looking at if a home was burglarized, or how much damage there was done to a certain house or household, or a person's rating of their safety in their neighborhood. Might depend on things that predictors that apply to them as a person. There might be predictors that apply to the neighborhood as a whole. Okay, I'm seeing some of these thinking lines. What are you guys thinking about? Carter?
One thing I was wondering is when we talk about the predictors or IVs being measured at all of the levels, I think I'm having a hard time wrapping my head around, like, how do you even like present or break down something that's being predicted at all the levels? Like
The predictor
like,
can come from any level. It doesn't have to come from all of them. So if we have gender, that would apply to each individual. But if there's a neighborhood watch, I mean, each person lives somewhere that has a neighborhood watch or not, but the neighborhood watch status would apply to the whole neighborhood. So a level 1 predictor in this scenario would be gender, or how much money they make, or ethnicity, something that applies to just the person specifically. It would be a person-specific variable. But something that pertained to the whole unit, the whole neighborhood, would be a level 2 independent variable.
I think
pertains to. Yeah, Michael?
I think I understand Carter's confusion. He's thinking, so if you read this, that last line, at any / all of the levels, I think Carter might be thinking that there might be a variable that comes from all of the levels at once, whereas the text means you could have predictors from all the levels, but they're not going to be the same exact predictor.
Yeah, so you can have socioeconomic status is something you could have measured at both levels. So you could have socioeconomic status of the person, specifically that person, and you could have socioeconomic status of the neighborhood as a whole. Like, is it a closed neighborhood? Is it a trailer park? Is it a gated community? Something that would pertain to the whole unit would be measured at the level of neighborhood. So if the next bullet point on here says pupils in schools, so sometimes we want to know, say if we're looking at math achievement, we're going to look at this example coming up, the math achievement of kids in a school. So our level 1 micro units are the individual kids, but they exist in the hierarchy where different kids are kind of clustered or already exist in these groups called schools. So each school is the big unit, and within each school, the little units are students. So the lower level one is students, the higher macro unit is schools. Socioeconomic status could be defined as how much money each kid's parents make, but usually in real life, we can't get a hold of that information. But what we can get a hold of in education research fairly easily is public knowledge, is the percent of students in a school that get free and reduced school lunch. And that can be a marker of socioeconomic status of the whole school. Even though socioeconomic status really pertains to individual families at a certain extent, we might only measure it at a school level because that's all we have access to. So if my kids go to Sunrise Elementary School in Smithfield, and it's a walking school, so all the kids walk, so it's fairly homogeneous compared to a lot of elementary school areas, and they have a very low percentage of school lunch there. But within the school, there are some families that are better off than others, but we can't ask or get that data at the individual level, so we only have it for the school as a whole. Carter, does that help understand how independent predictor like socioeconomic status would only be measured at one or the other level?
It does help. I think it just makes me more curious when we get to interpretation, presenting those results, where it's like, how do you present influence from multiple levels at once, I guess. But
we will, and sometimes
like
we do things like group mean centering and grand mean centering, and we'll see that. So sometimes it's how, now if we talk about math achievement for kiddos, does individual households' income matter for how well kids do in schools? Yes, but even if I'm really, really poor, generally I have a poorer outcome scholastically because I don't have as much going on for me. That's been shown over and over again. But what if I live in a school district that has a higher average household income? Does this education you get depend on not just your socioeconomic status, but the whole school? Because if your school is in a wealthy area, they have a bigger tax base, they've got usually higher level teachers, less attrition of teachers, they have more resources, after school programs maybe. So the socioeconomic, it might matter what my household's income is, but it might also matter what's the income of the school at large. And teasing apart those differences can be complex, and we're going to see an example of that when we get to group and grand mean centering. And sometimes we want to show that, but we're unable to because we only have a global school-wide variable instead of being able to get that individual fine-grained detail. The worst case scenario is to have a global variable and pretend like it's an individual level variable, because then our standard errors are going to be screwed up. The betas themselves might be accurate, but the standard errors will be wrong, so our p-values are going to be who knows where. Okay, so here's a picture of the kids in class. So this level 1 are the individual students, student 1, 2, 3 in class 1, and then another student 1, 2, 3 in a class 2. And so the classes, now in this top picture, each class has a totally different color, a dot. Is it usually like we have the red class that are all 100%, the green class that's all 90%, the blue class that's all 50%? No, they're spread within class that overlap, but I've just shown them in different colors for illustration. But this would be one way to show it. This bottom diagram with the level 1 at the bottom and level 2 at the top, this is a frequent way we display multi-level models to conceptually develop what goes where, what are our levels, where do our variables, our outcome and our predictors belong. So I'm just going to touch on longitudinal data. So longitudinal data, the math is the same, but in hierarchical, usually people are the lowest level. People belong to bigger clusters, groups, or organizations, or geographical locations, or something. In longitudinal research, the person is not the lowest level. The observation time points or conditions are the lowest. Observations on a person are the lowest level. So person 1 might have 5 type points, and person 2 has their 5 points, and on and on. And when we do this, we say that person is then the upper macro level 2 unit, and those observations are nested on a given person. And so the level 1 units are the observations that are made at different time points. And because of the difference about people being the lowest level and people being not the lowest level, we usually will do the chapters and the example problems and the homeworks a little bit separately, because even though the math's same, it gets confusing if you try to do them at the same time at first, even now. So you can have situations where you have both hierarchical nesting of clusters and longitudinal repeated measures. So I might have people that exist in groups called neighborhoods, and then I'm also measuring them at like 1990, 91, 92, 93. And so we have repeater measurements on people, and the people belong in group. Education, a lot of times we have, end of level scores for like 5 years in a row. So you can have those repeated measures on people, and then the people in groups, and then the people would be the middle level. There's not one way to go. That's what's usually referred to as a panel design, when you give the same thing to the same persons year after year after year. We can also rearrange what is the units of the different levels. What if this is a repeated cross-sectional design? So what if I went to different neighborhoods at different years, but the people are not necessarily the same each year? So in that case, we could, instead of having individuals as the middle level, we would define individuals as the lowest level, grouped at time point, coexisting in a neighborhood. So when you get to 3 levels and more, it can be more complex, because what is nested in what depends on the study design. And then also later on in the book, we will get there, we talk about cross-sectional designs, and this can fall in there as well. But we're going to just stay with 2 levels for right now to simplify, but it can expand up. Anyone have any questions? I think this is about the end of this. So this is like a more complex one. Is the brain throbbing yet? Okay. So here is another example. So I might have a treatment that I want to test with subjects through their therapist. So I would randomly get not randomly, but I would get some therapists to help me out with my study. And then each therapist would ask some of their patients, if they would participate and have IRB and clearance and informed consent and all that. So we have, in this case, to simplify it, we have 4 subjects, 1 subject per therapist, and then half the therapists are giving the treatment and half of them are doing the control or treatment as usual. This way it's lined up. We are then also going to follow the subjects at 3 time points. So we'd have repeated observations made on each subject. The subject, usually we'd have multiple subjects per therapist, but a therapist is either giving out the treatment or the control. So this would be a case where we don't want to have therapists do both the treatment and control, because it might be confusing or hard for them to administer both at the same time. We do this a lot with education. We randomize not the kids to get the treatment or intervention, but the teachers to give the intervention or the control, because it's just harder to do it the other way around. So in this scenario, treatment or control would be assigned to the therapist as a whole, not to individual patients. The patient gets whatever their therapist is giving out. And then in the education, that's often, we don't randomize Johnny, Billy, and Susie to get treatment or control. We randomize Mr. Smith and Mrs. King, and their whole class gets it. So this is the quasi-randomization is a multi-level design, and it should be analyzed as such. And when you don't, you're disaggregating even if you don't know it. And education is wrong a lot.
Sorry, I have a question.
Yeah.
So when looking at this is the therapist like bubble. Is the 3rd level like when it's with the therapist bubbles, is that like the treatment, or would it be
the
4
arrows
levels?
are kind of, they're using the same looking arrow for a lot of different things here. Treatment and control would be a predictor variable that is specific to a given therapist. And the therapists are the units of level 3, the participants or subjects are the units of level 2, and the individual observation points are the units of level 1. We're going to break down a lot of scenarios like this because it's not always clear from the beginning what's a level and what's a variable, and there's always more than one way to do it. And so you have to have a lot of knowledge about how a study can and was carried out to figure out what's a level and what's a variable and where it was assigned.
Thank you.
Okay. So graphically, I am a visual kinesthetic learner with dyslexia. It makes a good combination for statistics, right? So I'm very visual. So we're gonna look at some plots here. This is, let's see, look, this is the example going into it. So this would be the research question would be, let's see, I have individuals that are existing in neighborhoods. I didn't assign them to neighborhoods, they just belong to neighborhoods, just do. And my dependent variable I'm interested in looking into is a health score. I want to know about the health of people. So this poor health score is a continuous measurement that it's based on the questionnaire that I give to all these people. And I do it in some neighborhoods I picked out. And one of my main independent variables that I want to use to predict health is age. Health, my dependent variable, pertains to each individual person. Age, in this case, is being measured of each individual person. Now, it is true that there are some neighborhoods that have more elderly, especially now it's the fad to have these retirement communities. And there are some neighborhoods that are like more young families. But the way the study is being carried out is we are going to each person, we're asking their individual age and having them fill out this questionnaire so we can measure their individual health status. But they belong, they're not maybe the 100 people in my study are not independent, because how I picked those people was first I picked the neighborhoods. Out of all the neighborhoods in the state, I'm picking these 10 neighborhoods or 25 and then going into each neighborhood and randomly picking people. This is how they do political surveys too, is they pick regions and then districts and then neighborhoods and then people. It's a stratified random sample instead of a fully randomized sample. So in this scenario, the way I've just set it up, I have 2 levels. The lowest level is where the outcomes measured, that's our individual people. And then the level 2 macro units to which people belong to are neighborhoods. So we have a random sample of neighborhoods, but we really don't want to know about neighborhood Hallbrook Oaks and neighborhood Sunshine Terrace or whatever they're named. But those neighborhoods, even if they weren't really random, are standing in as a random subset of all possible neighborhoods I could have chosen. So usually when we do a study, you have participants in your study. Do you really want to know about how John is different than Tom?
No, not really.
Not really. Your participants, why do we have multiple participants? Why don't we just have 2 participants if we have a treatment and control?
So we can see trends in populations.
Because you know that there is person-to-person variability, right? So if I want to try treatment versus control, I could do sample size 1 of each, but maybe those 2 people are different just because people are different. So I want a good number of people in the treatment and a good number of people in the control so that I can control from person-to-person variability. That's the residuals. Controlling for person-to-person differences. Is there a difference between treatment and control? And so with multiple levels, we want to say, We know that there's neighborhood to neighborhood variation. We know there's person to person variation. We don't care what that is, but we want to control for it. So the multiple levels, we're controlling for person to person variability, and we're also controlling for neighborhood to neighborhood variability. So those units are random. The units in each level are treated as a random effect, but because we don't care about how those few are, we want them to stand in to represent a sample of all possible people in all possible neighborhoods. So we treat them as random. This random versus fixed is going to be a conversation we're going to have every class day from here on out. So the variable gender. If I've asked gender and age, say I'm going to do gender, and let's just make this really simple on ourselves. Let's just say male and female, just to 2 categories, just to make it simple. I'm not saying that's all there is. People would fall into one or the other category, but that is the full list of categories that I am going to look into. I care about the difference between male and female. I don't care about the difference from Tom and John and Sally and Sue, but because they're treated as a random subset of all people. But I want to get a beta for what's the difference between male and female. I want to get a beta for treatment versus control. So those things that we want to get a beta for, we actually want to study the full set of all the categories. We treat that as fixed. Units that are being treated as a random subset of all possible units, we treat as random. Now, questions?
So are you determining the things that you want to get a beta for, like based off of theory and like what you expect to see that are different? Sorry, my dog got mad. Sorry, everybody. But then the other things are just you're asking, like you need to know that information in order to control for the differences between.
Yeah. To be able to control from neighborhood to neighborhood variability, I need to know who's in the same neighborhood with other people in the same neighborhood, but it's not that I want to get a beta for what's the difference between Mountain Oaks and Hallbrook Creek. And I don't want beta for the neighborhood to neighborhood differences. I just want to control for the variability between neighborhoods. So the things that, the easiest way that I've found so far is if I want a beta for it, it has to be fixed. If I don't need a beta for it, it's random. That's the simplistic definition. So here is a very simple model. This is a fixed intercept, fixed slope. This is if I was doing single level regression, I would plot age and health, and I would get a scatter plot and I'd find the regression line. We just did this in homework 1, right? There is the regression line. This regression line treats health status at level 1 being predicted by age also at level 1, ignoring the fact that people are already existing in neighborhoods. So we get one line. What does this line tell us? If age is the x-axis and our y-axis is poor health, so the older a person is, the poorer their health. We get a trend line. It's positively correlated. But in this model, this is a traditional single level model, we ignore the fact that there are clusters of people clustered in neighborhood with a shared environment. Okay. This is a multi-level model. What do you notice about the picture?
There's a bunch of parallel lines at different intercepts.
We go from having one regression line to having a regression line for each neighborhood. So this is a two-level model where we just have random intercepts. So see how each line has a different up and down level, but they all have the same slopes. So the slope is fixed for all the neighborhoods are fixed to the same value, but the slope is allowed to vary between neighborhoods. Okay, so fixed slope, fixed intercept. Here we're allowing variation, random variation in the intercepts, but holding fixed or constant the slope. Okay, here comes the next one. Whoa, we get different options. These have random intercepts and random slopes, but there's a lot of different combinations. Panel C, all of those lines are positively sloped. So they have different intercepts, but some of them are flatter and some of them are steeper. So the way we could interpret this is the relationship between age and poor health is the strongest, i.e. steepest, where poor health rates are quite high on average. Because the higher the average is, so as those average intercepts go up, the higher average is paired with a steeper slope. So there is a positive association between intercept and slope. Higher intercept goes with steeper slope. See, the lines that have the higher intercept also happen to have the steepest slope. Panel D, what do we notice? As the lines go up, as the intercept goes up, what happens to the steepness?
Decreases.
They get flatter. So higher intercepts or higher average values are paired with shallower slopes or not as steep as slopes. So there's a negative association here. Higher intercept goes with flatter slope. So here we have a positive association. Here we have a negative association between intercept and slope. Now what do you look about E? What do you notice there?
And,
What's the pattern? There's complete crisscrossings. So the pattern is completely sporadic. There is no correlation between intercept and slope. So some neighborhoods have a higher intercept paired with a flatter slope. Some neighborhoods have higher intercepts paired with steeper slopes. There's no overall trend between the average level and the steepness of the slope. And F, the dark, can you guys see the dark maroon line on there? That's the average of all the average lines. It's the mean of the means. It can be meaningless. What's the slope of the, in panel F, it's F, yeah. What's the slope of the overall average line? 0. So overall, there's no association between age and health. But in the neighborhoods that have a high intercept, we see a steep slope. Neighborhoods that have a low average have a negative slope. So the association is positive for some or negative for others, depending on the overall average. And this is the situation where if you do a single level model, you'll run it and you'll get no association. There's nothing going on. But if you split it out and incorporate the clustering, not only do you find something significant, but we see a meaningful pattern. The idea here is it depends. The intercept depends on the slope depends on the intercept. It's cluster dependent. I'm going to skip the last of this. We're going to have a 5-minute break because I'm getting antsy and I can tell you guys are too. And we're going to come back. And when we come back, we are going to go to that second PowerPoint I told you we do. And this is where we're going to look at the equations. So you definitely will want to take a little break before we get the math equations. 5-minute break. Okay. I wish we could stop and chit chat because I'm sure your brains have been processing, but I will stay on after class time expires, but I do want to get through these equations. So we're going to go a little bit fast, but I will stop because I know just reading the Greek letters and notation in the book, not so user-friendly, right? Hawks is a good writer, but when it comes to algebraic formulas, it starts to get a little much. Okay. So for this slideshow, We are going to go through equations for 2 levels only. We're not going to tackle 3 today, just 2 levels. I know he did 3 levels in the book. We're just going to do 2. So let's start with what we know. Ordinary least squared regression. Homework 1. This is our equation, right? We have a y is our dependent variable that we're predicting. And in the simplest case, we have an intercept and say one independent variable x. We even color coded it fuchsia. So here we would have 2 betas. We call them betas because in the equation for the line, we use the Greek letter beta. Now, this will create the line of best fit, but do all of our data points fall on the line? Exactly. No. We have most of the data points are off of the line a little bit. I have a residual. So graphically again, now I usually means the individuals of the lowest level. So I would be like person 1, person 2, person 3, person 4, I being equal to 1, 2, 3, 4. So what's beta not? Beta with the little 0, that's our intercept. That's the y-intercept where the regression line hits the y-axis when we extrapolate it back that far. Okay. What's beta 1?
The slope.
It's the rise over run. If we run 1 unit in the x direction, beta 1 tells us how far up or down we would go in the y direction. That's our slope. Okay. And some points are off the line. The amount that a point is off the line, that's the residual. And we usually use this little Greek epsilon, little e with an I. Now, betas right now have a 0 or a 1. The beta 0 is for the intercept. The beta 1 is the slope for our first x variable, the only x variable we have right now. But that e has an I subscript because every point is off the line a different amount. So the residual is different for every individual. So the epsilons or the e's have a subscript I to denote that it's a different number for each person. Are we good yet? Are we so far together? Yeah.
Unless an individual has the same score.
Unless you have 2 people with exactly the same set of predictor and independent and dependent variable both. And that can happen, depending on the fine-grainedness of your measurement tool and the number of subjects you have. Yes. Okay. So now I've changed the equation a little bit. I've added on those residuals. The residuals have an I because the residual depends on who we're talking about. The X value depends on who we're talking about, and the Y value depends on who we're talking about. But the betas don't have a little I on them because the betas are summarizing everyone. What's the intercept for everyone on average? What's the slope for everyone on average? Okay. The single level regression. In single level regression, everything that has a beta is fixed. We have a fixed set intercept and a fixed set slope because we only have 1 line in single level regression. What we have as random is we say the residuals are random. And if we get into the nitty-gritty stats math formulas, it's written like this. E sub I tilde wave is distributed as a normal 0 sigma squared E. What this means is all of our, and usually above that tilde wave, they write IID, identically and independently distributed. This is the assumptions of simple, ordinary least squared regression. Our residuals are independent, normally distributed around the mean average of 0, and have 1 variance value that is homoscedastic at sigma squared E. That's our variance of our residuals. That's 7610 in a nutshell. Now we're going to blow it up. Okay. Now in single level regression, we're saying everyone comes from 1 single population. We have 1 simple random sample. So we have 1 intercept and 1 slope. To go to multiple levels, here's a picture. What if, this is simple, we only have 2 groups? In the first panel, our two groups have roughly the same slope, but they have different intercept values. In the second picture, our two groups have different slopes, but somewhat similar intercepts. This is where we consider group to group difference on top of person to person difference. That's what makes this a multi-level. We have person to person differences at level 1 and group to group differences at level 2. I'm not talking about treatment and control group. I'm talking about classrooms, therapists, natural hierarchical clusters. So if we have multiple groups, each group can have a slightly different line. It can be different in the intercepts, or different in the slopes, or different in both the intercepts and slopes. And Carter, you asked, how do you know what's fixed, what's random? The answer is it depends. And we already stressed how you can decide, but it is complex.
Just in the example you just gave, you said that treatment versus control wouldn't
Fixed, because we want to
be fixed. Okay, is there a reason? Is that always the case? And is there a
if
reason?
you want a beta for it, you have to treat it as fixed.
Okay.
So if your research question is about, and if we're asking a research question about a certain intervention, we are pretending like there is this intervention or not this intervention, and usually those are the only two options. They are not two options out of a random, they're not a random subset of all options. When we choose subjects and we choose groups, those are usually chosen somewhat at random, or at least they're supposed to be representative of all people and representative of all neighborhoods or schools, even if we didn't really get it randomly. There's always some level of convenience. Okay. All right, so let's change up our formulas. Okay, I have made a table for the formulas that are in the book. On this side, we have LM. This is a linear model. This is single level, ordinarily squared regression. On this side, I have a linear mixed effects model, abbreviated LME. These abbreviations are different depending on who you talk to, and I will use them different. I'm sorry, it's just all over the place. But this column is single level regression. This column is multiple level regression. Okay, so I is for individuals in level 1, the micro or smallest units. Level 2, we use J, because I and then J. J is for level 2, the macro groups or the clusters to which the I units belong to. Okay. Okay, so here is, let's just do intercepts only. So notice at the top, these are empty models. We have no predictors in here, just to keep it simple to start. And we're just thinking about intercepts. Here's our single level. This is the equation we saw in the previous slide if we take X out of the fact. So we just have one intercept. Where are the I's? Individuals have different Y values and different residuals. Okay. There is only one intercept. Now this is where we introduce this gamma. Gamma is this Y-ish looking, this is little gamma. So there is only one gamma. Now this is kind of pointless here, because in single level regression, we are saying there is only one cluster. It is the population at large. So there is only one fixed intercept. And so it seems silly that we're going to replace beta with the one gamma, and all we've basically done is swap gamma for beta. That seems really, really silly, but hold on. Let's go to, so we're saying that there is one fixed intercept, and that's the population's grand average, and then we have residuals for one residual for each person that we're saying are normally distributed with homoscedastic variance sigma squared E. That's the variance of the residuals. Okay, I'm going to follow this and throw in the second level. Okay, the I's and the J's come out to play. Okay, let's start with the Y. The Y value, the dependent variable, depends not just on who the individual is, but on which group they belong. The residual depends not just on who the individual is, but also what group they belong to. Now the intercept. Before we only had one intercept, beta not. But now what do you notice about for multi-level model? This is random intercepts. What do we notice about the beta? There's not just one beta, there's also J. So there's a beta intercept for every group J. This is why we developed the gamma. So we say that the intercept, beta naught, for any group is equal to the grand average intercept plus or minus some disturbance. So there is a grand average, and that's gamma naught, but then there are group averages. Each group might be a slightly higher or lower on average. If we think about kiddos in a schools, we have a grand average math score, but then each school would have a slightly different average that would be slightly above or below the grand average. Each group's average is a little different than the grand average. That's what intercepts. If you have an intercept only model with no predictors, the intercept is the grand average. But now here we're saying, and then I plug the gamma and the U in place of beta, and I get this. So we have a level 1 model and a level 2 model, and if you plug the level 2 model into the level 1 model, you get this full model. So here is the full intercept only model.
I have a question.
Yes, I gotta go back first.
Beta or gamma, the group average?
Gamma is the grand average. Notice, so here I have them highlighted. So gamma naught is the whole population's grand mean. And in single level model, we're just saying there is a population, but in multi-level model, we're saying there's a grand average, but then some groups are above and below that. And then within each group, each individual is above or below their group's average. So we're splitting up the residuals into the part that's due to group difference and the part that's due to person within a group difference. So when we did ANOVA, we took our sum of squares and we divided sum squared within subjects and between subjects. We're doing the same partitioning or dividing of variance up. So that's why these are sometimes called variance partitioning models or variance components models. So the gamma naught, when we do our models, instead of using LM function, we're going to use LME4 or LMER for linear, instead of linear model, it's a linear model mixed effects regression, linear mixed effects regression, LMER, instead of just LM. And we're going to still get the estimates, but instead of calling our estimates betas, we're now going to call them gammas, although I'll probably slip and call them betas. Those are fixed parameters. We also get random components, but we don't usually, do we usually publish all the residuals? We usually don't publish all the residuals. We publish a summary about the residuals or a plot of the residuals. The same thing with these random components. We usually summarize them by giving their variance component, how much they vary, rather than the actual values themselves. Okay. Should we keep going? Okay, these models have no predictors. They're just grand averages. So let's do a predict.
How did you predict, just, sorry, quick question. Considering the UOJ is the individual group difference from the grand average, correct? Is there a, I mean, I guess, how do you, is it as simple as, like, I don't know, like a standardized score off of the grand average, or just an actual, like?
Units are kind of arbitrary. The units are a combination of the predictor and the outcomes units. And we'll see this, again, we're talking kind of like conceptually right now. We'll see it in action in an actual data set on Thursday.
Okay. Yeah. Okay.
Well, he kind of talks about it in the book. He shows you an example in the book without showing you the software usage, and I think it's very valuable to see the software so you can see physically where the pieces are coming from. Okay, now we're going to do a predictor. Now at the top I have diffusia X, and I'm saying X is fixed, meaning we want a beta for whatever this predictor X is. So in regular regression, or here is, So we have random intercepts model, random slopes, or random intercepts and slopes. And they're abbreviated RI for random intercept, RS for random slopes, and RIAS for random intercepts and slopes. Okay, that's the next slide. We'll get there. So random intercepts. Okay, I want you to look where the X is, the fuchsia X. If we're doing random intercepts, that means that which of the betas is for the intercept? Beta naught or beta 1? Which is the intercept?
Beta naught.
Beta naught is our intercept. So if we allow our intercepts to randomly vary from group to group, I'm going to put this J on the random intercept. Did I put a J on the beta naught or the beta 1? Not on the beta 1 because I'm saying it has a fixed slope but a random intercept. We have not even talked about why you would choose to do one or the other. I just want to see the equations for both of the options. We'll talk about Carter's discussion board question of why would you want to treat it random or fixed later. Okay. So compare the random intercept. We put a J on the intercept, but not the slope. On a random slope model, where do we put the J subscript? On the slope, but not the intercept. Guess what you do on a random intercepts and slopes model?
Both.
Both, okay? That's the level 1 model. So let's go to the random intercept. So we're basically saying that the intercept varies from cluster to cluster. So what a cluster's intercept is the grand intercept plus or minus a little bit above or below, depending on which J cluster the person's in. But the slope is the same regardless. There's no J's there. If we're doing a random slopes model, we're saying the intercept is the same no matter what. But the slope, beta 1, depends on J, which group you're in. It's the average group, the grand average slope, plus or minus a little bit depending on which group you're in. So this is how you would show the 2 level models. We have level 1 models and level 2 models for actually a set of 3 equations. And then we can substitute those beta equations in place of betas up in the top equation to get one combined model. I don't know about you, but I'd rather have 1 equation than 3. Who's with me? Okay, so here's the substitution. I'm using my colors because I'm visual. So each person I in group J's predicted value depends on a grand average plus or minus how much the group differs and a grand fixed slope and that person's residual. I can't, there, I thought. So in the intercept model, random intercepts model, we have a fixed intercept and a random intercept, but we only have 1 slope. For the random slopes, we have 1 intercept, but 2 slope components when we substitute it back in. The gammas are always going to be for fixed beta-like estimates. The EIJs, those are always the person-specific residuals. The U's are cluster-specific residuals for either the intercept and or the slope. So these final models here are the same as we would for regular regression, but instead of calling them betas, we're calling them gammas, and it depends on which book you read, whether they do that, even that. But the thing we're adding in are these U's, these group level residuals. And now the regular old residuals are how much the individuals vary from their group, and then the U's are how much the group differs from the grand overall. Now, there's also some stuff going on. So in purple, I've done the residuals. The residuals in single level regression are assumed to be normally distributed around 0 with a homoscedastic variance sigma squared E, sub E. Now we're adding in more random components. In orange, I have the random components. They are also assumed to be normally distributed with a mean of 0 and a homoscedastic variance, which we're going to call sigma squared of either U1 or sigma squared of U0, depending on if we're doing random intercepts. We're doing random intercepts, it's sigma squared U0, and sometimes people shortcut this to sigma squared 0 and leave off the U. I'm sorry, it's not consistent. And for random slopes, the U is for the random slope, so it's sigma squared U1, because we use a subscript of 0 for an intercept and 1 for the slope. And then there's a covariance that we have to worry about, which is usually assumed to be 0. Okay. I'll bore you with the details, but here is the workout for random intercepts and slopes. What do we know? We have a fixed intercept and slope. Those are the gammas. Now we have random intercepts and slopes. Those are our orange U's. And then we have our regular old residuals in purple. So we assume that our sigma squared E, our residual variance, is centered at 0, equal spread, and same with our U's. But in this green over here, the covariance, whether the covariance is positive, negative, or 0, those are the panels at the end of the figure on the paneled figure on the end of the last PowerPoint. Okay. Here they are all laid out together. At the top, we have a single level equation. In a single all of these equations we're predicting Y. In the single level, we only have I's, we don't have any J's because we don't believe in any clusters. But in the multiple level equations, we have I's for the individuals in J cluster. We still are predicting Y, we still have our residuals. We almost always have a global intercept and a global slope. That's the gammas. The multi-level model question is, do we add a random intercept or a random slope or both? Okay. Here's another picture. We have I micro, oh, it took me off I was doing the, oh well. Highlighter. Okay, so the micro units are the smallest units, being people. Each person has an outcome, and X is usually used to represent a predictor that is person specific. And then we say person I is nested or belongs to cluster J. The macro clusters, we usually, for the predictors, use a different letter, because why not, right? We usually will use a Z to show that the predictor does not belong to individual peoples, but that predictor was measured at or pertains to, belongs to the clusters as a whole, instead of people within the clusters. I've gone over time 3 minutes. I tried to shove it down your throat really fast. What say you?
That was really good.
Yeah, I think I want to just stare at it more, but I don't know that I need it to be explained more.
Yeah, this is going to take some digesting. This is not stuff that you see once or like, got it. Well, I'm sure there's someone like that, but not me. We will be doing examples. Examples are the only way you can really digest this. The math gets kind of heavy. The good news is you don't have to do any calculations. 0 calculations by hand, not feasible. You just have to know which variables you want fixed, which variables you want random, what are your levels, and how to tell the computer to do it, and how to interpret what it spits back out at you. You don't have to know how to do the math. I don't know that I know how to do the math.
Is that, I guess one thing I was definitely fuzzy on, are you going to have to know in order to run this, like what random intercept situation versus a random slope situation is? I mean, I guess I see the
In real life, you have to decide. Now, Carter asks this exact same thing on the discussion board. How do you know if it should be fixed or random, intercepts or slopes? The best I can tell you is theory. And sometimes you can try different models and compare which one fits better. But that is often limited in power by your sample size. So it's always better if theory can guide you, but you can fit competing models, fit a random intercepts model, fit a random slopes, fit random intercepts and slopes, and compare the model fit to see which one fits best. The only problem with that is sometimes we're limited in power due to sample size. So it's always better to let theory guide you. This is why you do a lit review. Very, very much scenario dependent. That's why we have to do examples. All right, yeah, that's basically it. That's a good slide.
I'm sorry, Sarah, I have to go now.
Yeah. Oh,
but
holy, you guys are like 6 minutes over. Get out of here.
thank you, bye.
But just for chit chat about this, because I'm weird.
I was wondering why the use of the term disturbance instead of error at the group level is that it seems like obviously to distinguish that it's group level, but it seems like there's more to.
It is a group level error, but it's not. The word error can be problematic because it's not error as in it's wrong. It's just natural person-to-person variability fluctuation, natural group-to-group variation and fluctuation. So the word error has this like negative, it's bad connotation. So that's the word disturbance is used because it's just different. But that doesn't really have the right context either. The verbiage around this has been developed by mathematicians a lot, which is kind of clunky.
Well, I think it's neat that it's not called error because error is just something that you haven't explained with your model.
Well,
right?
and group to group difference, you have no control over how strong the clustering is. Like how much, the proportion of variance, how much variance is person to person variance versus group to group difference. You have no control over that usually. It's just inherent, and it's a nuisance that we want to control for. But you can't change it, and usually we don't even really want to study it that much, but we want to leverage it to get a more accurate model to explain or predict or both.
I have a quick question.
Yeah.
As we can enter the predictor in level 1, can we enter another predictor in level 2? I think this model we don't enter any predictor in level 2.
No, but the next slide, this slide. So this slide where the X is a level 1 and Z is a level 2. So you can make it more complex. I didn't hit this slide in class, but definitely. In fact, it is often the case that we have level 1 predictors and level 2 predictors, and we want to know how they interact with or moderate each other. How much does the group variable moderate the person level variable? Or how much does a person level opinion moderate the treatment or personal history moderate the group level treatment. Those are the cross-level interactions, and they're very much often the point of our research.
That full model equation only has one predictor at each level, and it's
Yeah.
that complicated, right?
Yeah, and you can flip through here to find much more complicated ones. The point of this slideshow was not to show you how complex it can get, but to show you where the bits and pieces fall from.
Sarah, this might help me clarify, because I've been like trying to think about it through this lens. Like I'm trying to write up analysis where it's a treatment study, but a subset of the participants, they actually had a choice between the two treatments, and then the other ones were randomized. So I was trying to set up the levels where like one level is whether they had, let's say like level 3 is whether they had a choice or not.
Okay,
And then
I'm
level
going to
2,
stop you right there. If you want a beta for it, it's a fixed factor, not a level. So if you want to know if they get a beta to know what, or in fact, you want an interaction between treatment and choice,
exactly.
then you want those to be fixed factors, and those would apply to the individual. Whether they chose it or were randomized to it would be one predictor, and whether what they got, the treatment or the control, or which treatment, would be another predictor. Now, was the treatment or the intervention carried out in a group setting?
No, individual. It's online self-help, so no.
Yeah, so that may not be a multi-level model, because this is a key point. For it to be a level, it has to be groups or clusters that you have a good number of. If you only have 2 groups, it's probably a fixed factor.
Yeah, yeah.
If you have 2 or 3 groups, you probably want to treat it as a fixed factor. Usually you would have like 10 or 12 or a good number of clusters.
Okay.
If it's a few groups, it's almost always fixed.
Mm-hmm. Mm-hmm. So what would be an example of like a random in that, and what I said? I guess if that's like a random effect, if those are the fixed effects.
Yeah, so you might have so random effects are structural in the intercept, and then they can also be in the slope in structural. They can use, so you have random effects. The U's that we've seen so far are for just the structure, basically. We have, well, no, the U's, we did get a little bit with the variable, but sometimes they're random slopes with the variable, is a very random variable. I think come back Thursday and we'll look at an example.
Okay.
That's a better thing to do instead of me trying to think on the fly for that.
Yeah, that's helpful. I think for me, it's like, I'm trying to like, cause I've been like working on that like specific problem for so long that I'm trying to like let go and just like understand this more from the ground up. So
yeah, it is good to think of it in terms of what you're already doing, though. I mean, that's a good lens to learn anything is how do I put this in the scaffolding I already have?
Yeah, yeah. Because Tyson, like he helped set it up as like a multi-level model, and like we're working with that, but I'm trying to like understand how and why. So yeah. Thank you.
Sure. Jill, you were looking a little concerned. Is this hard and heavy for you today?
I think I just get that concerned look when I'm digesting.
Okay. And I won't be, I get worried. I'm like, I want to help her.
No, I'm just staring at the numbers, trying to work it all out. But I think I just need to do a little more staring.
Okay. And the examples will help. It's very dense, and you can't, it's like learning R. You can't ease in. You just kind of have to go, here we go, and dive in and just kind of doggy paddle until you start getting your bearings.
Well, and I really want to be able to like, obviously I don't need to know how to calculate by hand all of this, but I at least want to understand like a basic level of, I don't know, just so I can at least like explain what multilevel modeling is.
And I want you to be able to read, and that's why this next homework assignment, you're going and finding articles in your area to see, because if nothing else, I want you to be able to read those articles at the end of this class and be like, ah, got it, yeah, that made sense.
I want to be able to do a step, at least a small step above that, which is that I want to understand all these I's and J's. Like, I want to understand what it's actually doing. You know what I mean?
Mm-hmm.
Like, anyway.
Yeah.
I had another
see the example.
What?
I think Thursday's example will help.
Oh yeah, I've been dying for an example.
Yeah. So I would definitely read through because we're going to do the exact example from chapter 2 in this book.
Okay.
It goes through chapter 2 and 3, I believe. And it's a good example of a lot of concepts. So I would definitely, if you haven't already, read chapter 2 definitely before class Thursday.
Perfect. I'm like halfway through at this point.
Uh-huh.
I have another question that's related to I know that you don't plan on like really fully explaining the assignment, which is fine, but for getting data, I'm not sure how to go about doing it because there's specific data that I want to use for my dissertation. They won't give me the restricted data until I have IRB.
So you're probably not going to be able to do that in the time frame of this class. So we could do a couple different things. One, I could generate, if you could show me what the variables will, I could generate some data for you.
Okay, well, I'll be able to get access to the unrestricted data. I mean,
if you have, the thing you need to know here is you have to know who belongs to which cluster. You don't need names, so it can be de-identified, but you need to know the like subject 1 through 10 are in cluster 1 or group 1, and whatever de-identified.
I don't know if they'll.
Yeah. So it might be more realistic for you
in the fall, but I don't know. I keep checking and it's not there yet.
Okay, so you don't need to panic yet because you won't need to have this like starting to nail down for like 3 weeks at least, like till we get into October.
Right. I was just thinking that if I needed IRB, then
if worst case we can find a different data set,
right,
that you can practice on. Because it might be unrealistic to be able to do it on like your dissertation analysis for the class project.
Of course. Well, I mostly just wanted to like play around with that data for the class.
And a lot of people have, but it just depends on the timing.
Yeah. Well, and when I found out I needed IRB to get it, I was like, oh, well, that's not gonna happen unless I like did some other project with it first and then.
Which maybe we could look at, maybe there are enough variables in enough clustering aspects. Is it repeated measures or is it clustered groups or both?
It could be, I could get access to repeat. No, it's inherently not. It's the AIRS. Have you heard of AIRS? It's just a teacher survey about curriculum. And they do it every year, but I don't know.
So if it's not repeated measures, then it would, to be multi-level, you need to have some clustering or hierarchical. So do you know like teachers which teachers are in the same school or district?
I know for sure that the restricted data would have that information. And it's definitely like across the United States. So there's going to be, state
number.
Yeah, there's going to be tons of levels. So definitely a robust enough sample, but.
Yeah. Well, let's keep me updated as the next like 2 weeks progress. And if it's not looking like it's going to come through, then you might need to do something different for the project just so that you're not doing it like I'd hate for you to wait and have it come out like the week before it's due. I mean, there's no way.
Of course.
That would just be insanity. And I don't want, like, you can't start on the project now because you guys don't know enough yet.
I'm sure,
You
yeah.
know what a multi-level data set could look like, let alone how to start modeling it. So we have to wait till we get enough experience to kind of know what might be a feasible project. But I don't want to wait till like the last 3 weeks of the semester because you'll never have time.
Right.
So.
Okay. Well, and because the data's not released yet, like if the data was released, I would be like more than tempted to try and start like a different side project, a pre-project. But how crazy would that be to try to do?
Depends on scope, how prepped the data is, how much time you have to spend on it. There's a lot of variables.
I mean, to get through IRB right now.
Well, there are some pros and cons. I don't know how they'd shake up in your case. I mean, the pros is they're not, a lot of projects are dead in the water and people are waiting to see when the restrictions lift. So they're not like constantly looking at as many ongoing projects that are active right now. But there is the IRB person that's housed in our department, her office is across the hall from me. She got reassigned because she's one of the only people on campus that had certification. She used to do genetic studies. So she has human subject stuff with genetic samples or human subject samples. So they pulled her over to do the COVID testing because they had been having the ag laboratory handle human subjects. And that's not a minor thing to do COVID tests here on campus.
Yeah.
For not just research, but for like testing students at the student health center. And so she got pulled off. So like, they're kind of slow, but then they lost a person. They're trying to hire some more, but they might not be totally trained. So I don't know what to tell you on how fast it will go through.
Okay.
I would definitely nudge them. I know that if you go to the IRB website, they now have a Slack channel, I guess. And definitely email and kind of probe and say, hey, you know, this is accent data. It's already been collected. I just need permissions and it's okay, you know. So you should be, what is it? Oh, let me stop the recording.
Oh, good idea.
Oh, that stopped sharing. That wasn't exactly what I wanted.